Okay. So I talked on Monday about the inclusions of anti-self-dual connections into all connections. And now I'd like to talk about a sort of geometric problem that has a lot of similarities to this. Like this problem, which has its physics name is gauge theory, this, the problem I have is today's problem is called the sigma model. And so today I want to talk about the inclusion of holomorphic maps. Okay. Into all maps. So I'll just put map. Okay, so there are a few bits of code in this. First of all, sigma is a Riemann surface. Genus G, and in fact, most of the talk, mostly just the Riemann sphere. X is going to be a variety. It's going to be typically a rational one. I mean, always rational, in fact. Always here. It's going to be a rational variety. And in fact, there's going to be varieties of a special type. The reason, basically, is you want, if you want to study this space, you want there to be lots of maps. And if the space where you'll find lots of maps will typically be a rational variety. Star just means these are base maps. So they take a base point to a base point. There's going to be, K is going to be a multi-degree. And typically, it's going to lie in Z to the not K. I'll try to say, I don't know, let's say L. And in fact, it's going to be, the degrees are going to be positive. So it's be in the positive L tent. Okay. Now, I was saying there are lots of points of resemblance. The first is there's a natural functional of a map, which is just the L2 norm of the differential. So you're supposing you put a Kähler form here, and your Riemann surface also has a metric, which of course is in the, I'll just say Kähler also. Okay, so you know how to take the norm here. And the critical points of this energy functional, are called harmonic maps. Critical points. And basically the only thing you really want to remember about this is if there's a holomorphic map, they minimize energy. In the homotopy class. Okay, so if you've got, if there's one holomorphic map, then your minima will be holomorphic. The other thing that's rather like It's like the L2 norm of the curvature for the instanton problem. It's not a good functional for Morse theory. And it's sort of bad in exactly the same way. So there's bubbling, and this time you actually see the bubbles. Okay, so if you take a minimizing sequence, so here's sigma, and I'm just going to try to draw its image in X. So I've got my fixed Riemann surface here, and there's some patch here that's being mapped to X, and I'll just try to give you an idea of the image, and this sort of you get a bulge, and basically as you go to a limit, the following can happen. Doesn't necessarily, but it can. This little disk here gets smaller and smaller, and the image gets bigger and bigger. And in the limit, just have a point here. And so what's happening here is a point is somehow has expanded into a sphere. And it's actually pinched off. Okay? And rather like the instanton, this actually eats up a homotopy charge, if you want. Okay? So they really are bubbles, and in fact there's a theorem of Parker and Wolfson's. If you do the full limit is a bubble tree. So in other words, you have a sort of body where the genus lives, and then you'll have a bunch of spheres, and you can get spheres on spheres, and little pimples elsewhere and things like that. Okay, that forms a tree. It's in some ways, again, there are sort of similarities between what happens here and what happens in the sort of stable maps for Koncevich's sort of compactification, or the Mumford. Well, it's the stable maps for the sort of Gromov-Witten invariance.
This is taking place in X.
Hmm?
This is taking place in X.
That's the image in
That's
X.
the image in X.
Yeah. Now you see, it's not really an image because all of these spheres here are images of points. Okay, so you're seeing it, if you want. It's in some sense it's the limit as a, I don't know, some current or varifold or whatever in the product of the source and the image. Okay, so anyway, you're seeing these things, but. Okay, but again, often you have a limit theorem. That tells you that pi j of the based holomorphic maps of degree k of sigma in X is equal to pi j of map k star sigma in X. For j less or equal to some linear function of k. Now, k here is a multi-index, so you just take k to be the minimum of the ki's, and you've got this is some linear function. Okay, so that's the sort of general behavior. Now, again, what's happening here is this space is constant. It doesn't depend on k, really. It's the same space all the time. And this space, as you increase k, it's getting bigger and bigger, and it's gobbling up the topology. Here, for example, the homology groups, they're often, almost always, non-zero in an infinite range. And here, of course, these are essentially manifolds or manifolds with singularities. Okay. So when? For what x? Okay, so basically, known if there exists an action of a solvable group, solvable connected group, complex group, n on X, with an open, dense, free orbit. Okay? So in other words, you can think of is some equivariant compactification of n. Okay. So you've got this group that's basically, I mean, it's not necessarily abelian, but it's, if you want in a C infinity sense, it's a product of C stars and C's, basically. And this thing has an open dense orbit, and it's lying in X. So what are the examples? Well, flag manifolds. Okay, so you take a vector group, you quotient by parabolic. So for GLN, P is basically something that's block upper triangular. And you've got the unipotent radical, or it's I don't know, a U bar, whatever. It's sort of mirror here. Acting, it doesn't matter, really. So just say U, the unipotent radical, acts. Take U. Okay, so that's a case where the group is actually nilpotent. Okay, second example, toric varieties. And so n is just C star to the n. There are things called Bott-Samuelson varieties. These are, you take a bunch of parabolic subgroups, in a reductive group, and then you act by the Borel subgroups basically on sort of consecutive pieces here, and then a final one that's acting over here, and then you've got B acts here, and you can find basically a N sitting inside B that acts freely. Okay, certain, but a large class of spherical varieties. So it gets a little bit technical, but G acts on X, again a reductive group. You want P B has an open dense orbit, I don't know why I'm saying open and dense. Anyway, there's an open dense orbit. It's not necessarily free, but you can sort of fiddle around under certain conditions and find a subgroup that actually acts freely. You can take equivariant blowups. Of the above. Okay, so if you take a flag manifold, take a Schubert variety on it, because you're looking at the B orbits, blow it up, and you're in business. Okay, so you can get things. Now they're all rational. They all have a group action, so they're not. They're all kind of special, but basically, you'll see why. You need a sort of handle on this problem, and there's a sort of trick that makes this very explicit. Okay. So how can we attack this problem? Well, let's go to a case that we know and love, which is just an example. I'm going to take x equals p1 and n equals c. So here, p1, of course, is c union a point at infinity. C acts additively on c and fixes the point at infinity. Okay, so and the basing condition, I want maps from, good point, sigma equals p1. Okay, so the basing condition is, I just want, say, infinity mapping to 0. Okay. Now, basic fact is you can write any such map. So, quite explicitly, it's a sum, I equals 1 to L, AI of Z minus, say, BI over Z minus BI to the, say, KI, and K1 plus KL is the total degree K. Okay, so here, what have I got? The BI's are distinct. The degree of AI, these are polynomials, is less or equal to Ki minus 1. And you've basically written out the arbitrary map from the Riemann sphere to the Riemann sphere here. Okay. So, of course, the AIs here are the principal parts. And the BIs are, of course, are the poles. And it's this sort of pair of descriptions, this description that you want to get. Okay. The first thing you notice is the description is somehow stratified. It's stratified by these multiplicities. The generic stratum will have distinct poles, and then the more exceptional strata will have the poles with higher multiplicities. Okay. But first I want to define a principal part at, say, BI equals 0. Okay, so principal part at, say, B equals 0, or Z equals 0. Okay? Now, this is a sort of truncated map truncated map, a sort of minus k z to the minus k, so I'm just writing a pole at 0, plus a minus 1 z inverse. And why is it truncated? Okay. Well, if I want to write the set of these things, so set of principal parts at z equals 0, it's going to be the set of truncated maps, like that. And I can think of it as maps a minus k z to the minus k z to the minus k plus a minus 1 z inverse plus a 0 plus a 1 z plus blah mod the additive action of maps into C. A0 plus A1 Z plus blah. Right? In other words, I can apply a map into C that normalizes this bit to 0. Because it's the action's additive. Right? Maps into P1, mod maps into C. Okay, so more generally, if U is open, you can define a pre-sheaf. Okay, so you define the principal parts on U. So open in C, say, or P1. Well, say P1. Okay, principal parts on U. Well, it's going to be the meromorphic maps from U to P1. Okay, so here I just mean that meromorphic is, well, what is it? It's meromorphic as a map. How do I say this? It has poles of finite order, and it's not uniformly, the image is not uniformly in infinity. Okay, so there's a certain number of poles, it's a discrete set, and those poles are of finite order. Okay, and I define the meromorphic maps modulo the holomorphic maps from U maps, and this is the quotient sheaf. Okay. So, if you want, you get an exact sequence. Now, what's an exact sequence in this category? It's a sequence of pointed sets. You see, there's the trivial principal part, right, where there's no pole. Okay, so and so you get a sheaf. Maybe I should say a little bit more. You get a sheaf that looks somewhat like the sheaf of divisors, right? They're discrete things. They're just supported at points. And it's a sheaf whose sections are almost everywhere 0, but have a sort of certain number of points where they're not. Okay, so you get an exact sequence of the holomorphic maps from U into C. Yeah, okay, so U to C. And this, of course, is just the OU to the meromorphic maps, U into P1, to the principal parts. And the configuration of principal parts is just a section in H0 of P1 P. Okay. Okay. Now you don't want to pole at infinity because of your basing condition. Okay. So apart from that, so it's a section of P1. So in fact, it's a section on P1, but its support is in C. Okay. And when will this come from here. So let's call my section S. Okay. S comes from a map if and only if delta of S. So I take the coboundary. I've got an exact sequence in cohomology. This sort of peters out at H1 or 2 or something, but there's enough structure here to get me to H1 of at least the first one. H1, P1, O is 0. But this group is 0, right? There's no H1. So always. And concretely, if I take a principal part, I write it. Okay, so I've got a principal part. I take representative sort of elements, represents principal part. So I'll cover P1 with open sets. So I've got disks UI around each of the principal parts and a big open set U0, which is a complement of the points. And basically, I can take a holomorphic map on the punctured disks because it's meromorphic. It's holomorphic on the punctured disk. And I take F0I represents the principal part, and then I just write out a cocycle. F0 is F0I plus Fi. And you see this is the map. That's the map. And then this is the adjustment to the principal part. You have to sort of play with the tail here to make it the global map. And so you phrase this. Of course, you could just write it out this way. But you've sort of gone around this sort of funny way. And basically, by sort of in a sheaf cohomology version, you've written out your map. Okay. And so, and the key point is this H1 vanishes. So maybe just case 2. Okay. Case 2 is well, sigma equals P1, X equals P1, and the group N is now C star. Okay, so P1 is then C star union 2 points, 0 and infinity. Okay, and again, you look at the principal parts of U will be the meromorphic functions on U to P1, mod the holomorphic functions on U to C star. And now you want to think of, remember that C star is acting multiplicatively. So if you just look at 0, for example, you're getting a map that looks like this: A minus K, A minus K Z to the K minus K plus K plus 1, Z to the minus K plus 1. Okay? And you write this as Z minus K, A minus K plus A minus K plus 1Z plus blah. And you see basically that acting multiplicatively, you can kill all this. So you can just kill. In other words, what killing means here is just turning it to 1. So in other words, this is the same as Z to the minus K. And so basically for a principal part with a C star action, the only information is a degree, a number. Okay, so here, It's just a degree, right? So belongs to Z. Okay, and indeed, of course, the same way, if you look at S belonging to H0 of the principal parts, then you take its co-boundary, it will belong to H1 of P1 with O star. And this, of course, is Z. Okay? And delta S will be 0 if the sum of the local degrees is 0. Okay, I cheated with my basing condition here. I didn't cheat, I didn't tell you what it was. Infinity should map to 1. Okay? If the sum of the local degrees is 0, i.e. same number of poles as zeros, counted with multiplicity. Okay, and indeed you write out, I don't know, f of z, has the following way. Ci. Okay, so you can write out an arbitrary map that way. Okay, and then I obviously didn't take into account the multiplicities, but basically, as long as your configuration of points, as long as you've got the same number of factors above and below, the limit will be 1. So you respected your basic condition. You've just written the map down. But again, sort of cohomologically, you could go through this thing with some multiplications, and you're getting the same idea. Okay. So now do the general case. So general case. Here, if you want x, what does x look like? Well, x is a box, but it has n here, and then it has divisors at infinity. So what number did I use? Okay, so L divisors, or L varieties at infinity. Okay, L orbits, L codimension 1. That's the best way to say it. Orbits at infinity. And then the varieties, of course, are closures of these things. Okay? And so, again, you write out principal parts of U will be the meromorphic functions, U into X. So a meromorphic function is one that is sort of whose image lies in this, and it doesn't live in the infinity. It sort of moves around like that. Okay? Now, you see, its image could just lie in this open cell here, but in this open cell, you can use the n action to just bring it to the base point, which you always take inside n. On the other hand, if it hits this divisor at infinity, the best it can do is sort of move around like this and get normalized transversely. Okay, so there's a the ones that hit infinity sort of have to get caught on it if you want. You also see when there's several divisors at infinity that you can have sort of this has multiplicity, say 1, 0. This would have multiplicity 0, 1, and then you can hit both. Then you have multiplicity 1, 1. So the multiplicity is an invariant that is there's several numbers associated to it. Okay, so principal parts will be quotient by, again, all U into n. And as I was saying, S belong to principal parts of U, okay, or, well, I just take the limit. So S belong to principal parts. has, over the point x, has a multiplicity. And the multiplicity basically is you can write it as a relative cohomology class in H2 of Xn, homology class rather. Okay, so it's you've got a little disk mapping into here, and that little disk is defining a relative cohomology class. Okay. And again, if you take a section, well, you can add these classes up. So in other words, if you now have S belong to H0 of, again, I'll just take P1, the principal part sheaf, you have its multiplicity, which will belong to H2 of Xn. And basically what happens here is you'll have the meromorphic functions. Let's see, what do I want to say? Yeah. Okay, so I'll have the H0, the meromorphic functions. Okay. That, well, it's a meromorphic function. It's a function of the sphere into this variety. It has a degree. That degree will give you a class in H2 of X. H0, the principal part space, will have a degree, but that's a local degree. It's in H2 of Xn. So the relative homology. And this, remember, there was a co-boundary here, and it's going to live in H1 of the group. And here, of course, there's a boundary, and it'll live in H1 of N. Okay? And so you're seeing obstructions here to it being a global section is that this map here has to be 0, and in the case I just did here, basically it was just saying you had the same number of zeros and poles. So there's sort of local degrees, but some of these divisors at infinity are equivalent under the n action. And so there's a sort of sequence like this. So you're only interested in configurations of principal parts that are somehow balanced. But apart from that, the statement basically is that's all you've got here. See, as I was saying, this is a bunch of C stars and Cs. Now, it's a solvable group. It's not abelian. But you can take a filtration and sort of work your way up the filtration and use basically that H1 of P O is 0 and H1 of P of O star is Z, and show that basically this is an isomorphism here. So as long as you take your configuration of principal parts to be balanced in that sense, then you're in business. You get a map. Okay. Again, as I was saying, there are various features that are very similar to what we had on Monday. So maybe features. It's one, they're stratified. Okay. So stratified by multiplicities of the principal parts. Okay, that's the way I should say it. So the space of holomorphic maps into X stratified by multiplicity. So in other words, generic is simple poles. Codimension 1, double poles, or one double pole, and so on. Okay. This is actually quite important because it's what allows you to, when you're studying the topology, to see that it stabilizes. Because as I was saying on Monday, on this generic locus, a lot of the topology is just generated by points, the poles moving around, if you want. And that imposes a bound on the cycles you create, and shows basically it stabilizes quite quickly. If you were just in stable, simple pole situation, the homology, the stabilization for pi j would happen basically for pi j would happen at level 2j, so degree 2j. But then you have to worry about these higher codimension strata. And that's okay because they're higher codimensions. So when you're building up the homology in the spectral sequence, they get sort of lifted up and they're put out of range. But you want that codimension to increase. Otherwise, it just doesn't work. And so in analyzing these things, because there's, in some ways, well, those who've worked on these things, the structure of Schubert varieties they're not, for example, for the flag varieties, they're not smooth. And so there's a little bit of messing around with desingularizations to see that there is a sort of increase in the codimension. But it's not, well, it requires work. Okay. So the first thing is they're stratified by multiplicity. And the second thing is there's a stabilization map. Where you just add a fixed multiplicity, well, I'll just put one principal part. Okay, so you have here's your base point, here's infinity. You don't have any principal parts here. You've got a cloud of them out here. So there's none around infinity, so there's a well-defined space to sort of put in a principal part. So here's infinity. You've got your 4 already, and you just glue in an extra one there. And you can glue in one of each type in a little cloud. And you'll always have some extra space in your infinity to sort of glue more and more of them in. Okay. So in other words, you get, and this obviously preserves the stratifications. In other words, these are basically the same as over here, and you've just added in something of multiplicity 1. So you get stabilizations that things of degree k, things of degree k plus 1 in this sort of generalized sense of, because it's a multi-degree. Union of the strata k1 to kl, so these things, and it's mapped to union of the strata k1, kl, and 1. Okay, so you've got a multiplicity pattern. These are all vectors, and you're adding in this vector 1, 1, 1, 1. Okay, so you add it in here. Okay. But then, as I was saying, you get a spectral sequence H star of the strata H star of Hall. Okay? So that's the sort of picture that comes in here, and it of course sort of strata for k, strata for k plus 1, all k plus 1. And then, as I was saying, there's a sort of an accountancy of cycles. So that a class of dimension j requires at most 2j points. Okay, and this is classical results from these people in the 60s and 70s were looking at symmetric products, labeled symmetric products, and they sort of come up to this conclusion. And it's basically, in other words, you've got the low-dimensional strata have a lot of these sort of simple poles, if you want, and if you're building up strata, you just have to use those, and adding in that extra pole, it only sort of changes the homology in high dimension. So the low-dimensional homology is already stabilized on these strata. Now, you could have, instead of a bunch of simple poles, you could have a very high, sort of squidged up multiplicity, high multiplicity pole here, but that is, the stratum that contains that is a very, very high codimension. Okay, so again, for the low-dimensional homology, it doesn't appear. So it sort of balances these two phenomena, and then you get the stability result for homology. Pi j, again, you work with covers, and that's actually the hardest part of this business. But you get that the homology stabilizes. Okay. So A star of mk stabilizes, and pi star. And the question then is to what? And there's a very nice result of Dobson, and it was a student of Grain Siegel, and I think used ideas that Siegel had already developed. And what he does basically is say, okay, if the as long as U has a boundary, in X, then the holomorphic maps to X are basically the same thing as the regular maps in X. And that's basically the Weierstrass approximation theorem. But of course, it's as usual, it's like building a Roman arch. You know, there's that last little stone that has to be put in. It's that detail. It's the worrisome thing. And in fact, what they do is they build, if you want, putting in or filling in into P1. You have to sort of build a mapping telescope. So you have this sort of thing that sort of, I don't know, so map. And you exploit these ideas linked to quasi-fibrations, and it's one of those things where every time you read it, you say, wait a minute. But it works. It just looks somehow that you're getting something for free. But so you get a limit, and maybe I'll just do the algebraic thing. And what you get basically is you'll find that the map K and somewhere out here is map infinity. Okay, and here will be the mapping telescope will be Hall infinity. H star is here too. Okay. Oops. Okay, so you get this long diagram. Basically, the bottom, it's isomorphisms all the way. And at the top, it's stabilizing. And then basically, from this telescope argument, he's getting the equivalence at infinity. And so the two, that gives you the result. Okay, so you get this picture. I should mention that a lot of people have worked on this. There are various people. So the techniques I talked about were the ones I understand. You can also show that, so maybe I'm in the sort of remark stage. So maybe remarks. Well, the first remark is if you use sigma instead of P1, it's okay, at least for n nilpotent. I did that one. You can perhaps do the general case. I must admit I didn't try. And the reason is basically that you're looking at a stable object, and the obstructions are sort of finite dimensional. And so you can sort of homotope your way around them. Because it's just you've got in other words, you'll have a huge number of poles and points. Okay? You can, it doesn't quite work that way, but you can sort of delegate G of them to deal with the obstruction to the existence of the map, the H1 if you want. And then the rest you can sort of build classes the way you want. I mean, that's not the sort of formal thing, but it's sort of that idea. The second is that if you take infinite dimensional flags, you can do instantons. So there's this idea due to Atiyah that MK of, well, I'll just say for S4 group, so these would be G instantons for G, your favorite compact group on S4. This should be the same, basically, as the space of holomorphic maps of degree k from P1 into loop G mod loop G plus. So these would be this is the loop group based on, maybe I'll put a complexification here. Right? So compact group, take its complexification, take the loops on it, quotient out by their Fourier series, so quotient out by the positive frequency ones. Okay, and you get a flag manifold. And basically you can apply this whole principal part technology to this, and it's essentially the idea I was outlining, except it works for arbitrary groups. So that was a recent paper with Michael Murray. So you can do this and finishes off. It also does some rather nice cases. So it works for instantons, and if you generalize, go to another loop G mod parabolic, you can get a similar stability result for what's known as calorons. And these are sort of instantons on R3 across a circle. They have, the boundary conditions are not the, well, sort of special boundary conditions. But anyway, these things are, you can also think of as monopoles for the loop group. So you can get the at least some of the cases known. Maybe conjecturally, where is it true? Conjecturally, I'd say if X is rationally connected. Should give you this stability. But I think it's certainly necessary, because to explore the space X, the maps go everywhere in X, right? The C-infinity maps. So you have to at least be able to sort of reach all parts of the space for this to happen. On the other hand, getting getting anything remotely resembling a proof is kind of difficult. And this is, and maybe I'd just like to finish with some unfinished business, which is just to comment on the role of particles. Particle descriptions. There's some classical, i.e. 1960s, descriptions of function spaces that are very, very close to what I want to talk to. So I'm just going to restrict to X equals P1, okay, which is the two-sphere. Now, if you're talking about the degree K maps in the two-sphere, it's useful to think of the Hopf vibration. And that gives loop 2 of S3 mapping to loop 2 of S2 mapping to Z. Okay, so this is the twofold loop space. So in other words, maps of the two-sphere, base maps of the two-sphere into S3, base maps of the two-sphere into two-sphere. And of course, these have a degree, and that's what it is. So the degree 0 maps, or the fixed degree maps, just think of loop 2 of S3, which is loop 2 of the twofold reduced suspension of the circle. Okay. Now, this has the May-Milgram model. And what you do is your source, you think of your source two-sphere, and you say what the map is on this. Well, you choose K points and put little disks around them. Okay? And then you map into the twofold suspension. So this is the loop 2 bit is over here, but the twofold suspension. And here's where my graphical capacities are going to be sorely taxed. You map it like this. So here's a circle. And then you've got your, let's see, I don't want to draw this. You've got a plane sort of coming through this point here, right? And remember these points, you put an element A in S1, B in S1 on associated to each of these disks, and here's your map A, and basically this is the map of the disk. So this disk basically here sort of expands out and reaches this infinity. This is all the base point. And all of this, all the rest goes to the base point. So you have a map that is spending 95% of its time at the base point. And then at these exceptional points, remember you're looking at the two-fold suspension of the circle. So there's a little plane through each point of the circle, and the ends are scrunched, and the base point is all scrunched together too. And so at these points, it just whizzes through, goes through once, goes through once, goes through once. Okay, so that's the model. Well, you see, this is very close to at least the generic stratum of holo. Okay, where you have points labeled by elements of C star instead of the circle, but it's the same idea. There's, of course, the way these strata glue together are totally incompatible, so it's not terribly useful, but it's somehow suggestive. There's another model that in some sense is even nicer, due to Duza-McDuff. Where you have positive and negative particles that annihilate. You don't get loop 2 of S2, but you get something close. Okay. And that one's even more suggestive, because somehow, if you want the physics of it, should be that you have a sort of Dirac sea, a sort of fixed positive and negative particles. And remember, variationally, remember you had, if you want, map bar rotation had these bubble trees in them. And if you could sort of include these bubbles, now of course each time you put in a bubble you increase the degree. So you need positive and negative bubbles, holomorphic, anti-holomorphic. Okay, but if you could build a model like that, and then you might get something for which the Morse theory actually worked. In other words, you take your map and you force it down, and it becomes this sort of small holomorphic map, but it's got this infinity of little particles that's sort of sitting in it that are taking care of all the topology of this big mapping space. They're just particles moving around. And then you've got the holomorphic piece. And as you increase the degree, the honest-to-God holomorphic ones are able to do more and more of the work. If you want, you go to another sector in this sort of Dirac sea. You increase the virtual. So you've got infinity negative particles and infinity plus 1, positive ones, and so on. I mean, they're details. Anyway, I think it's a sort of intriguing idea that at least includes or justifies or explains the sort of role of the particles. You're seeing it come up in a whole variety of contexts, but somehow they're details. So anyway, thanks for your patience. Yeah. Yeah.
See, this MK, the space of instanton,
Yeah.
is it closed under stabilization? I think
Close under stabilization.
is it closed under stabilization?
Well, yeah. If you describe it this way, you just add in an extra principal part. In terms of Monday's lecture, you add in an extra jumping line. Okay, so that's the sort of link to this picture. But it's adding in an extra principal part of fixed degree, so you can stabilize within the stratum, as opposed to doing it. See, it's this funny thing where there's a particle. You've got a particle picture on the nose. Remember, you're on P1 cross P1. Okay, so really the instanton should be particles on the four-dimensional object, but they're sort of fuzzy particles. And the addition sort of takes you a little bit out of the MK, right? Okay. On the other hand, if you have this sort of projected version of the particles, which is actually on the nose. And the two are homotopy equivalent, basically, but they're sort of, but you've lost a lot of the thing. And in fact, Ben Mann and Milgram, I don't know if Boyer was involved. No, Mann and Boyer actually looked at sort of homotopy operations using the techniques that these guys developed. All the sort of homology operations. They sort of looked at instantons and maps from this point of view. And you can build a lot of the unstable topology in a very concrete way. So it's actually quite a useful tool, but you don't get, if you're doing it on the nose, you just have the sort of 2 dimensions to move around, and you've lost the extra 2. So you lost a bit of the richness of the particle picture. Okay. There we go. Anyway, thanks again.